So now let's think about how to actually do differentiation, right? So in the previous video, we said that we are going to need to take the derivative of our frequency modulated signal in time. So how do we take the derivative of a frequency modulated signal in time using some circuits? First, let's consider the ideal case, then let's look at the actual case. So if we look at a table of Fourier transform properties or operations, we can see that if we want to do time differentiation, this is going to be the same as multiplying in frequency by some term j2 pi f raised to the n. Now, we just want to find the first derivative, so we'll set n equal to 1, and we'll see that if we want to find the derivative of the frequency modulated signal, we're going to need to multiply the frequency modulated signal by j2 pi f in the frequency domain. So how should we do that? Well, if we have a transfer function, j2 pi f, and we put a signal of the frequency modulated signal through some transfer function, we'll get h of f being multiplied by the frequency modulated signal. And if h of f is equal to j2 pi f, we can see that this is going to give us the derivative of the frequency modulated signal in the frequency domain. Now, what does the frequency response of this transfer function look like? Well, let's consider the relationships at the bottom, and we can see that the magnitude response is going to be equal to 2 pi f, so some constantly increasing function as frequency goes up, and the angle is going to be constant at pi halves. So now we have this relationship, and we can see that if we pass a frequency modulated signal through a transfer function that has the frequency domain response of j2 pi f, then we will be able to get the derivative of our frequency modulated signal. And the response of the ideal differentiator, so this transfer function that takes the derivative, is going to have a frequency response where the magnitude is going to be a line that's constantly increasing. So as f gets larger, the magnitude response is going to continue to get larger, but the angle response is going to remain constant at pi halves. So the higher the frequency, the more the amplitude increases for this transfer function. So are there any practical circuits we know about that could approximate this ideal differentiator? So are there any circuits we know about that could maybe just approximate it even just at one frequency near the carrier frequency? Since we know most of the frequency domain information of our original message is going to be centered around the carrier frequency in the frequency modulated signal, maybe we can just start out by finding a circuit that approximates this just at that frequency. So actually, there are a lot of different circuits that we could use that have a fairly linear sloped line as the magnitude response. So let's start by considering just one of them, and that's the high-pass RC filter. So the RC filter that looks like this is actually a high-pass RC filter. I see that I have that written incorrectly. I apologize for that. And the high-pass RC filter is going to have a transfer function that is the impedance of the resistor divided by the impedance of the resistor plus the capacitor. And if we change this using the impedance, we can get a frequency domain response that looks like this, j2 pi f RC over j2 pi f RC plus 1. Now, if we were to consider a situation where the value of 2 pi f RC was much, much smaller than 1, we could approximate that the frequency response is going to be equal to just j2 pi f RC. And so that's pretty close to what the ideal differentiator looked like. So if 2 pi f RC is much, much less than 1, then the transfer function is going to have a frequency response, J2 pi FRC, and the magnitude response of this is going to be 2 pi FRC, and the phase will be pi halves. Now, if we compare that to the original ideal filter that we looked at, it had a frequency response, J2 pi F, with a magnitude of 2 pi F, and a phase response of pi halves. So these are very similar. The actual high-pass RC circuit just has that extra RC term. Okay, so if we look at just the part of our high-pass filter that's near the carrier frequency, we could easily see that we could design a high-pass filter so that it has a magnitude response of 2 pi f RC that is nearly linear at the carrier frequency that is the same as our frequency modulated signal. And so for some frequency range, it might not be a big frequency range, but for some frequency range, our high-pass filter is going to appear to be very similar to an ideal differentiator. There are some other methods that you could use to do practical differentiation of these frequency modulated signals. This method is called slope detection, and that's because it relies on the slope of the transfer function of some circuit that you create. So we looked at a high-pass RC circuit, but there are other types of circuits that could also have a slope that is quite linear near the carrier frequency. In addition to the slope detection method, you could also use a balanced discriminator method, which might use multiple slope detectors. Or there's also another method called zero crossing detectors, which basically detect how often the signal is moving from positive to negative in the time domain, and that's going to give you some indication of the frequency. And that is related to this idea of using frequency counters.